So the last thing we got is safe transfers. This looks like Stuart Popejoy.
All right. Next up, we have Stuart Popejoy, and he's going to tell us
This is
about
2017.
the really cool contract system that he is working on at his new company, right?
Yep.
All right. Take it away, Stuart.
All right. Hi, everybody. Oh, thanks. My name's Stuart Popejoy. I'm with a startup called Kadena, I formed last year. And I'm going to be talking about a language that we built in Haskell. First thing I want to talk about is what are smart contracts and why do you want to use them? Why do you want to program in them? There's a lot of smart contracts are things that run on blockchains, but I kind of want to zoom out of that for a second and say that what you can do with smart contracts is you can build a simple solution, as in you've got a business problem that somehow involves 2 or more people working together. Maybe they're adversarial, maybe they're not, and you want to represent interactions between those people in the simplest way possible. You can make that solution into a service. The idea being that now the idea is that you can offer this to any number of people working together in a particular kind of interaction. You can run, the blockchain part of this is that you can run this on a trustless system in the sense that now you don't have to worry about kind of locality, like, oh, my service is over here, but your computer is over here, or your mobile phone is over here. This thing just kind of runs. It's like the next version of the cloud. Of course, that means you're going to want to make an API out of it. And, you're going to want to make it extensible. You're going to make it easy for people to integrate into that system. And once you're done with all that, the idea is that you're going to make some money. So that's kind of the developer story for why smart contracts exist. So why a new language for this? The point is that when you model something that way, there's not that much you want to do. You basically want to authorize things. This is something that Bitcoin did very well, is make it possible to authenticate and authorize. You want to, the other thing is that you really want, a lot of what you're doing is modeling something in a database. You want to make it really easy to say what your various kinds of data types are and how you store them and what the rules are for changing those. You want to do very little more than that because that way you can make it a safer environment because we're trying to do something in a trustless situation. So safety is important too because you don't want a bug in your code to make it that somebody can do something they're not supposed to. You also want to develop rapidly, and also in the notion of safety, you want to make it really easy to understand so that people don't have to like exercise their brains and maybe do something wrong. So simplicity here is not just like, oh, I want to attract dumb developers to work on this platform. Simplicity is I want to enable people to do the right thing. And, and then, along the way, I want to make it really easy to develop things quickly and make it that you can, do things like write APIs. So in the smart contract space, there's a language called Solidity that is the kind of leading language right now. There's a number of reasons why it's unsafe. One is that it compiles to a very low-level bytecode substrate that is basically a free-for-all of old-school registers and memory locations. So, we all know, this is worse is better all over again. We all know that that kind of environment is very hard to secure. It's also very general purpose. It's the opposite of the philosophy I was describing. You can do almost anything in it with modulo the fact that it's deterministic. It's an object-oriented metaphor, which is, to our mind, a lot of what we're doing is trying to make business interactions happen, so we would like to see something more like SQL. Of course, it's a mutable language, kind of along the object-oriented thing, so all the risks you run into when you can reassign variables. It's also slow, very hard to use, and it has been, there's been a high-profile $50 million attack to one contract. There was a vulnerability revealed in November.
Sorry, guys, I'm going to make you listen to that twice.
Modulo the fact.
I need to hear what he said there because I got to write it down. Sorry.
Environment is very hard to secure. The kind of leading language right now. There's a number of reasons why it's unsafe. One is that it compiles to a very low-level bytecode substrate that is basically a free-for-all of old-school registers and memory locations. So, we all know, this is worse is better all over again. We all know that that kind of environment is very hard to secure. It's also very general purpose. It's the opposite of the philosophy I was describing. You can do almost anything in it with modulo the fact that it's deterministic. It's an object-oriented metaphor, which is, to our mind, a lot of what we're doing is trying to make business interactions happen, so we would like to see something more like SQL. Of course, it's a mutable language, kind of along the object-oriented thing, so all the risks you run into when you can reassign variables. It's also slow, very hard to use, and it has been, there's been a high-profile $50 million attack to one contract. There was a vulnerability revealed in November or December that was unfixable in existing smart contracts, so safety is an issue in this space. So why this language that we call Pact? That's the name of the language we wrote. Our ideas about what a safer language is one, that it's interpreted. That means that, at any point in time when you're talking about what code is going to execute, it's the code you wrote. It's not some lowered version of it. It's safer also in this idea that we got from Bitcoin of that it's good to have something that's Turing complete that will always terminate. It's simpler in that it really just tries to do database and authorization and a few other things. It's safer in the sense that it doesn't allow you to reassign variables. And lastly, it's easier in the sense that once you write code in this, you get an API out of it for free. So that's kind of trying to talk about the motive. One of the things I'm trying to talk about here is that Haskell is this amazing, we built all this in Haskell, and Haskell is this amazing language for writing languages. That's why I'm trying to get into really the motivations and the design of this, so that I can empower all of you to think about how you're going to use Haskell or OCaml or any of these languages to write languages that don't necessarily look like Haskell or OCaml, and why would you want to do that? So as I said, Pact is a interpreted language. We feel like that since a blockchain is kind of a live code environment, something where you're throwing code out there into a system and it's executing, that it's good that that be run in an interpreter as opposed to have some kind of compile phase. We picked Lisp as the syntax, and one reason why is because that way the code actually is, fairly close to a lowered representation of the AST already. A lot of languages get lowered into something that looks an awful lot like a Lisp, so why not just make it a Lisp? But since it's interpreted, you can use a REPL. It kind of makes for a nice development experience. The only question about an interpreted language is types. And it's not an answered question that types are better with interpreted languages. So that's one of the questions I want to discuss here about a language design. The original Pact was untyped. And this was also because I wanted developers to use this language, and I wasn't really interested in Haskell developers. I was interested in business developers and people who are going to look at something like types and be like, "Wah, I don't want to deal with types. It's going to slow me down," this kind of thing. The other thing is that it was very important to have a language that potentially business people could read. I mean, if you think of something like Excel, or there's other languages out there that really kind of live the dream that the user doesn't have to be technical. That is something that we believe we can achieve with this language, which is not necessarily that a business user can write it, but that a business user can read it, because that's very important if you're talking about a shared computing environment. If you want to have assurance, one of the things is you want is to be able to essentially be able to look at the code and say, I think this does the right thing. So the whole idea that devs don't like types, this is the whole dynamic versus static debate. It's a little bit of a boring debate, but we launched off being like, people are going to be happier without types, and let's go with that. That was Pact 1.0. However, one of the things we realized once we realized that we were Turing incomplete is that we can probably, and actually based on a conference at last year's Compose, where a guy basically took a little mini language and stuck it into Z3 with a really small amount of effort, we're like, we could probably compile this to SMT-lib2, but then we have a problem because it needs to have a type at that point. So we decided to build a little Hindley-Milner type inference system into the and make it so that we could spit out something that was very strongly typed and throw it over to the SMT-lib2 compiler. So what was interesting about that experience is that we were writing a type checker that wasn't for the runtime environment. We were writing a type checker kind of just to have a type checker and also for this one particular path in the tool chain. So what we ended up doing is exposing the type checker to the tooling. So a weird thing about Pact that I'll show you if you look in the runtime in like Atom or something, we're actually working on Pact is, here's an example of a typical kind of accounts smart contract, which is something that basically allows you to like debit, credit, you can create an account, you can transfer. cetera, et cetera. You can do all the usual kinds of things you do with a cache module, an accounts module, something like that, a Bitcoin style use case. One of the ways you work in Pact is you make this thing called a REPL script. .pact is the language. .REPL is something that's got the way the REPL works, incidentally, is that it gives you some extra functions that allow you to simulate a blockchain. So the most interesting thing in here is this command, the type check command. So if I comment this out, and so the way this editor works, by the way, is it runs that REPL script if it sees one in the directory on your code. So it's a way you can write. It's a way you can do like test-driven development and things like that. So if I turn off type checking, I'm now doing a development environment that's not telling me anything about my types. If I go back into my REPL script and turn it back on, and then go in and refresh this, then all of a sudden I've got these type errors. And the idea here is that so if we look at where the types are in this code, what's interesting about Pact code is that it actually has type inference. And so I've got a few type errors, and we'll talk about exactly what those are. But basically, like something like a very important business function like transfer doesn't have any warnings on it because it's able to infer the types. So here's an interesting thing about creating a database language with type inference. Is guess what? Guess where I do have types all over the place? I have them in the schema for my main accounts table. So I've got decimal, string, key set, time. And then I just to kind of show that we're living in a hybrid world, I left type off of data being just a blob where you can throw whatever you want in there. So, and that's, in fact, all of our errors are coming from that data column. So if we get down to, let's see if this thing will just take me there. No, of course not. Let's see, where is it? There we go. Yeah. The warning here is that it can't determine the type on data because that's going into the data column, which is untyped. So this is just an interesting idea that like the type system is optional. There's another interesting reason for that, which is that you saw that we had types declared there, and now any code that touches that database is now typed thanks to the type inference. Those types that you declare in the code are remember, it's weird to have types in an interpreted language because if you look at what happens in compiled languages, of course, you erase the types by the time you get to something you're going to write. So in an interpreted language, what do you do with a type signature? You have to enforce it, actually, and you have to enforce an interpreter, which means there's a cost. So what's interesting with Pact having type inference is that you can apply enough types to make your code type safe, just as type safe as you want, and that will be enforced in the interpreter, but you don't overtype. So that's just something that's it's something that emerged out of our desire to do a formal verification. And that is a countdown clock cracked. I want to make sure our clock isn't freaky. I think I have 17 minutes according to that thing. I'm trying to go very fast here. I just thought that interestingly, that showing you that example of like typing the table kind of makes all the code typed. Just shows you that you don't necessarily think of SQL as a strongly typed language, but then it turns out it is because all the stuff that you're using is getting its types from the database table. And so you could think of it weirdly having a form of type inference. So anyway, so getting back to Pact's design, I already talked about most of the safety features that we think interpreted is safer. For instance, that vulnerability that came up in Ethereum in December, we would be able to roll out a new version of Pact. If we find a bug in the interpreter, and chances are we will, we can roll out a new version of Pact, and you won't have to change your code. Whereas in Solidity, everything gets not only does it get compiled down to essentially machine code, but it's also stored at a particular address. So there's really nothing you can do. So again, we call this single assignment. The reason why we don't say the language is immutable is because you've got this gigantic global mutable variable all throughout your code, which is the database. So, and we don't do anything funny with our database stuff. If you look at our code, you'll see that we're just doing CRUD, right? We have update, we have read. We have some interesting ideas about how to do databases right. Like we don't have any nulls. We prevent you from introducing any nulls in the database, but that's kind of actually classical relational database theory, is that nulls are actually a hole in the relational calculus. So that's just something we did to try to, so we have so we have this idea that we're turning incomplete. And also this idea that there's no catching of exceptions. The whole point of what you're doing in any Pact function is you're executing a transaction. That's an atomic transaction, and if anything goes wrong, by design, you can't catch that exception. It bails out, and your database is unchanged. The code style that it's trying to enforce is basically something where you're doing, where you're just enforcing things in a kind of, not a side effecty way, but like, something if you're in monad error or monad catch or something like that. The whole idea is that you basically want this kind of procedural metaphor where you're doing one thing, and the only thing that'll allow you to break out of that is if they're an error, and then it's game over. But of course, you get like nice error messages and things like that. So I'm talking fast because I only have 30 minutes, and there's a whole bunch of stuff in here. So again, trying to talk about this idea of like designing a language. What's interesting about something like smart contracts is why isn't it just a DSL? And what is a DSL versus a language? the idea here is that there are elements of this that really are DSL. So for instance, we have this very stylized idea about how you deal with public key authorization. So that, those are some custom functions. They're like little warts on the Pact language that show up as built-in functions. And then we have this biz DSL. We have this idea that there's this notion of enforce. You can enforce key sets. It throws an exception. Again, they kind of show up as custom functions. It's really a DSL. And then we have this key value database language. But as we've seen with something like SQL, you don't really need a full language. You could do that declarative. So the real way that this is a language is that we extend that key value metaphor about dealing with, so for instance, we have this notion of reading from a database by binding. And this is very much like SQL. We read from a database by binding variables to the columns in the database, and then those variables are in scope for that production inside of your Lisp code. We extend that notion so that you can actually take an object, and the idea here is that modules actually in Pact guard database tables. So there's a permissioning, there's a built-in permissioning that says you define a table within a Pact module, and then that table is only accessible from within that module, unless of course you're authorized as an administrator for that module. So what does that mean? It means that the module becomes the API for the database. It means you need a way to actually export rows out of your module. At that point, we needed to extend this notion of binding to database rows to binding to an object or dictionary style result. So that's where it starts looking like a language. And then finally, it's just to be able to do reusable computation. So for instance, in this module, we made a little function called, where is it? Check balance. And all that, that's a really dumb function. It's a really simple function. It's just making sure that an amount it's basically less than or equals with an informative message. But it also kind of illustrates this just as many types as you need. When we use the formal prover, we're proving on particular functions. So we don't really think we need to prove anything about check balance because you can just look right at it and see what it is. So we leave the types off there. But when this gets used in another context, it's able to say, oh, you're doing decimal, decimal, and it can give the type to the whole function. So again, it's this idea that you add just as many types as you need. So I wanted to focus. I'm going to get to the demo of the SMT lib stuff because I think is of interest here. But I also just wanted to talk about what it means to write a language in Haskell. As I've talked about, well, one, I think Haskell, and I'm not as experienced with OCaml or F#, but Haskell in particular is the easiest lang. It's like it's so easy to write a language in Haskell. There's so many tools out there for you. There's so much expertise there. But the thing to just keep in mind when you're writing a language for the general public is that it's still actually really hard to learn Haskell. So so just really think about whether or not you want to write Haskell for the masses, because there's Haskell for one. If people are going to write in Haskell, maybe they should write in Haskell. And if you're going to write a language, maybe you should write something a little easier. Maybe you should get out of your Haskell mode and think about something that's a little easier to use. And don't write Haskell in Haskell, in other words. That's certainly what we did. So anyways, I just want to talk a little about the types that we have in the language. So we don't do a lot of lowering because we want to maintain something that looks exactly like the code. But we do a little bit of lowering, of course. When we actually execute something, we do compile it. And actually, when we load functions, we go and aggressively resolve references. So term is the main type. It's a monad and traversable. It uses the bound library so that any var, so that whenever you have a var, you have vars and scopes, and it allows us to it takes advantage of the De Bruyne, is that the way? De Bruyne? Substitution. It gives us some nice advanced language features, which is nice because I'm not a PL guy, actually, but yet I've got really nice bug-free substitutions. That's really nice. So parsing is text to an expression. Compile is expression to turn name. Name is just a string, basically, but it can be a qualified name. Resolve is basically where we take a name and we run it in our eval monad and we get something, and now we reparameterize term to term ref. Ref is something that might refer to something that's already in the runtime. So now we've got a completely evaluated term that is actually already inlined all of its references. That's important again for the SMT lib. Eval takes term name and gets a term name out. By the way, an interesting thing about Haskell is that term name has a JSON representation. So as soon as you write a function and its inputs can be JSON, its outputs are JSON, it means you've got an API when you're done. So the type checker, again, is the one place we kind of do an explicit lowering. We make this very kind of like hard-baked AST. And the solver takes that AST. The only types we really have are those schema types you saw, where we're basically saying that it's a, it's where we have a columns, essentially. And that's what user type is, and that's what we pass into SMT lib. An interesting note we ran into that is kind of a, by the way, Pact is all open source.
Just need one more there, guys. Sorry.
Hard-baked AST, and the solver takes that AST. The only types we really have are those schema types you saw, where we're basically saying that it's a, it's where we have a columns, essentially, and that's what user type is, and that's what we pass into SMT lib. An interesting note we ran into that is kind of a, by the way, Pact is all open source. The interpreter is open source. All of the tools you're seeing today, a lot of the code is out there. And I say that because we ran into a problem, which was I had a type class for, we have a parameterized backend. The idea is we can run in memory. We can write to a SQLite backend, which is nice and fast. We can also have Pact run and write to Postgres, Microsoft SQL, anything like that. So we're parameterized over a database backend. Well, naturally, we initially did that as a monad transformer. And the idea that you plug in different monad transformers. We actually ran into some pretty serious performance problems doing that as opposed to making it just a dictionary of functions that we run basically in I/O. And with an mvar that we're reading. So that's how kind of, that might just be that we're bad Haskell programmers, that there's some nice way to parameterize a backend that is faster, but we actually saw significant speed increases by just running a dictionary of functions in I/O. So that was just an interesting kind of thing. The kind of libraries we use, I just want to give a shout out to all these because this is an example of how amazing it is to write a language in Haskell. Bound, really interesting library. That's what I talked about before. Trifecta is really useful because it has these type classes, token parsing and delta parsing, that make it for nice error messages and also kind of nice level of granularity. I actually wrote a delta parsing instance for AutoParsec, so that's something I should really contribute back. For crypto, we're using ED25509 Dana, which is screaming fast. There's the Cacophony library for symmetric encryption and noise protocol, which is amazing. Blake 2 for hashing, Snap for our APIs, and Direct SQLite for blazing. By the way, Direct SQLite, I really like that low-level interface, and I would encourage you to consider using that instead of using the more stylized one, because even though it's very much at the kind of low level, it's blazing fast. So just keep that in mind if you're ever doing this. We're getting low on time, so one of the things I wanted to do, there's some stuff about our system design. Basically, you have a blockchain, you have the Pact interpreter, and then you have the parameterized database backend. That's just a deterministic ledger. What does that mean? It means that actually Pact is designed to run in a single-threaded environment where the order of things happening is already determined. So Pact is not thread safe. That's something it is very much designed to be run in a single-threaded environment, and that's a good thing. That's not really a limitation. I'm going to skip over the database, talking more about the database metaphor, and show you how we're using Z3. Because again, we're using this smtlib compiling library. I should have put that in the library list. I don't know why I didn't do that. And again, the reason why we're able to do this is that we're already a form of single assignment semantics, or SSA. We have no recursion. Our code is once you load something into our environment, it already gets inlined, which is one of the things you have to do. Since we have no recursion, that's easy to do. And so we built this type checker to output a type JST, and that made it possible for us to start using. This is a little hard to see on the monitors, but basically, if you take a typical Bitcoin function, it doesn't turn into much more smtlib2 than this. I mean, there's more, but it's just interesting since smtlib is a Lisp itself. It was just kind of fun to see that we could actually do this in a reasonable amount of time. But one of the problems you run into when you start talking about formal verification is that we want to get formal verification to the masses. We want people to actually be using formal verification to make their code better, and that's a tall order because most people don't understand what formal verification is. It's just a very hard concept to understand. So remember what I said is that we don't have an immutable language because we have this huge global variable called the database. So what we decided was let's make a little DSL within Pact, doing a kind of doc test Python-esque thing where you put something in the comment to declare what you want to prove. And let's give you let's give you range stability, and let's give you mass conservation, which is basically a net zero kind of thing. We want to say that, this is an important thing in kind of actuarial land, which is you want to say that anytime you take money out of the system, you put money back into the system. We're calling that mass conservation. So let's look at how this works. We have a function here. We have a module. So Pact, everything is in modules. That's how you define a service. It goes on the blockchain. You've got this nice service. So maybe we have this account service. But here we're just calling an analyze test as the module. And we have a function called pay. And in the pay, we're basically saying that we're going to prove that the balance column conserves mass and that it never goes below 0. That's a very tangible thing that would be very nice to be able to say about your database because it's we're trying to keep track of money here. We want to make sure that we never double spend. And in this case, we don't want overdrafts. So we want to make sure that the balance column is always greater than 0. Of course, there isn't that much code, right? This is a really, really simple function. So duh. I mean, there's no bugs here. We have read. We have read. We have enforce sufficient funds. We have write. We have write. I can look at this code and I'm like, looks pretty good, right? But whatever, proving is cool. So we're going to prove some stuff, right? So here we go. So first, what we do is we do the compiler. So the compiler spits out smtlib. So it's going to capture every variable in there. I mean, this is another thing where Lisp is great because Lisp just makes scoping as freaking obvious as it could possibly be. So it's really just and by the way, we really are Lisp. We have let star with the whole confusion about whether to use let and let star. We have way too many parentheses. It's a real Lisp. So anyway, so we're going to declare all this stuff, and this is where the money part starts, right? So so we're using Z3. Z3 got open sourced by Microsoft about 2 years ago. It's blazingly fast, but it's relatively new on the scene because it was closed source, so people weren't using it in academia and stuff like that. But it's freaking amazing. I mean, what it can do in a very short period of time is it can basically simulate the entire universe of inputs and then try to break something for you. So what we're going to do is we're going to make assertions that we want it to prove false. So we're going to assert, in the case of conserves mass, we're going to take everything that represents a write to the database, and we're going to take everything that represents a read from the database, and we're going to add those, and we're going to try to say that they always have to be equal. And that's just a way to formulate mass conservation as a math problem. And we put not in front of it so that we say, Z3, tell us if this is ever possible that we could write the wrong thing to the database. Same thing with range. We're going to basically do an assertion of an or that any of these things that end up being updates to the database are we say greater than or equal to 0, and we put not in front of it. And again, we're going to call checksat, we're going to call checksat, and we're going to have Z3 ruin our day. So here we go. But remember, that code was great, right? We looked at it. It was awesome. It had no bugs. So here we go. So the first one, we conserve mass. We know how to write code. It's great. Unsat. Yay. Second one, sat. And in fact, this happened with this because this was a code the way it was in our open source repository. We're like, Z3 sucks, or we can't write smtlib. There's got to be a problem. No, our code sucks, actually. Amount. All you have to do is pass an amount of -1, and it's broken. It's a bug. It found a bug. Now, what's interesting about Z3 is Z3 doesn't give you the range of all possibilities. It's not a prover in that respect. It's not going to show you all the ways you're fucked. Excuse me. Screwed. It's going to show you exactly one way. It's going to give you a model. It's going to give you a model that says, here's how things aren't good, right? So -1. Well, what does that tell us? It tells us that we left an invariant out of here. So again, we have this thing called enforce. So let's go in, and let's make sure that our amount is greater than 0. Is it a decimal? I think it can handle both. There's a bunch of loosey-goosey stuff in Pact. We'll do coercions and stuff like that, because that's what C programmers are used to. And then we're going to say something like amount greater than 0, or amount less than 0, whatever. Who cares? By the way, this makes us better than Ethereum, the fact that we have error messages. All right, so are we in? Okay, so now we just make sure it compiles. We just put in that little fix. It looks like it compiles. So then we're going to pass that into ZM3 S3. Unsat, unsat. So I just want to point out, yeah, I mean, it's an amazing tool. I mean, it's really one of these things that, like, and this is something that we're working on actively to try to, like, make this DSL really big and obviously make it work over an entire corpus of functions. So anyways, I'm out of time. Thank you very much.
Wow.
Just questions, or is that it? Gershon, questions, or? Oh, OK. This person's close, sorry. No. One more question. I can make him quick. He said operational or free monads, and I said no.
Is there something like Ether that you can buy that is also like sort of pure?
Well, we're actually, OK, so that's a good question. Right now, this runs on a private blockchain, and the whole thing about a private blockchain is you know everybody who's there, so you don't need money, right? It just runs itself. You don't need incentives. A private blockchain is basically a BFT, like an SBFT or something like that. And you know, so the point is you're using public keys and leaders and all that stuff to guarantee consensus. You don't have forks. It's way faster. It's wonderful. But it means you can't have money on it. So one of the things we're doing is we actually are going to launch a public chain with Pact on it. And you know what a public chain means? That's right. OK. All right. Thank you very much.
That's so freaking badass. Like, oops. It's every single time we do this, guys. Every single time, I just get more and more bullish on Kadena. I don't know how you cannot. This is by far, like, what other blockchains do you hear talking about? Ergo, one of them, right? But so few. Cardano just wrote Cardano in Haskell. So imagine what Cardano would have been capable of if they would have rewrote their own coding language. Like, that is the secret sauce. That is what makes Kadena Kadena. Like, the few things that aren't ready, that need to be ready, like, you don't just rewrite your own coding language. You don't, you know, create a patent on the blockchain trilemma, right? You just don't do those things without having what it takes to deliver. You just don't. It might take them another 6 months to get things ready. Hell, I don't care if it takes them a year. We have nothing to, like, the only threat in reality, which wasn't even really a threat, but it would have been annoying, watching the entire market take off without Kadena. Because outside of Hopium, Kadena wouldn't, there's no catalyst that was going to drive it up. And there was nothing that was supported. Obviously, that was proven, right? Like, we knew when it hit $28, like, Kadena was going to free fall without DeFi. And that's what you need. And without NFTs and all the other incentives that you need to really, you know, take a blockchain to that next level. Like, I have to stop watching these videos because this is how I run out of money. This is legit how I run out of money every time. I'm like, I'm done. At first, it was like 5K. And then I hit that in the first day. And then I was like, all right, now I need 10K. And I hit that within a couple days. And then it was, all right, got to work to get to 15 because Kadena was getting awful expensive then. $20,000 here, you know, 20,000 at 20 because CADX was launching and DeFi was going to be popping off, right? 14 to buy more CADX because Kadena tanked out and I just lost half my bag. And then just it stopped at 8 or 10. And I'm just like, there is no way. Like, I can see it, right? So either like the VCs out there are just brain dead, right? Or they knew that I just can't wrap my head around seeing something like Kadena and not consistently adding more to more of my portfolio. There's a reason why you look on KuCoin right now and you see $2.4 million worth of limit buy orders going all the way down to 40 cents on Kadena. And then you open up AVAX and you see $33,000 worth of limit buy orders. Hey, have a good night, Nacho. Yeah, we don't need shit ready. We just need to make sure that when 2023 rolls out, because we need to be ready a little bit before the halving. Like, this is the time, right? This is when you break things. This is when you roll things out. This is when you build, right? But I like, as much as I get irritated with the fact that they don't have Pact ready or they don't have proper documentation, it just makes me think that Pact isn't ready, right? Because once it's ready, Like, I'm pretty confident that I'm going to be able to teach my 8-year-old son tomorrow how to write a Pact smart contract. He can walk through that test module and write a Pact. I would almost guarantee it. He'll do it. The thing is, does he have the attention span to like sit there and actually want to do it? For $50 in Roblox, I might be able to get him to do it. Might have to bribe him with $100 in Roblox, so we'll have to see. Enterprise are the backbone for Kadena.